So let's get this started. Thanks of you who are still in the room. I think you'll appreciate what we're going to talk about. So I think one of the highlights of today's talk is actually represented on this slide already, because you might realize that there is, two speakers, one being from BMW, the other from Merck. BMW and Merck are two large German enterprises, and if you know German enterprises, it's not easy to find common grounds to give joint talks, to collaborate generally. So yeah, I think this is actually it's quite special. To be fair, though, we are not really here to represent our individual companies, but to represent QUTAC, which is a German industry consortium. And what we want to tell you today is basically three things. First, what is QUTAC? Then, how does a industry consortium really produce something of value, which I think in itself is a very interesting question. And third, give you a very specific example of what a potential outcome of such a consortium is. And Alex is going to tell us about an application in generative modeling. Okay, then let's get started with a quick introduction to QUTAC. So in Germany, we're very privileged of having a very large funding pool to our disposal when it comes to quantum technologies. And you might be aware of the fact that a couple of years ago, over 2 billion euros were spent to foster fundamental research. And it is our firm belief, as large German enterprises, is in that the enterprises should have a word in how the money is spent, and make sure that the applicability and commercial use of whatever comes out of these research funds is actually granted. Which is why back in the day we founded QUTAC with the idea to really bring in that industry perspective by providing interesting applications to the ecosystem, in order to, in the long run, really kickstart that creation of a market, right? Which is crucial if you want to talk commercialization in the long run. QUTAC consists of 13 German corporations that really range a wide range of different industry sectors. As you see here, I think most of the logos should be self-explanatory. And the main takeaway here is, well, I mean, on the one side, we have more than, I think, 30% of the DAX represented in terms of volume. But more importantly, it's not more than 100 companies here. It's just 13, and we try to limit that number to not something too large in order to stay productive and to really be able to generate value. You might also realize that there is no quantum provider in the mix, right? It's really only applicants of quantum computing, which also is crucial for us in order to not throw money on the problem and not get our own hands dirty, but really make sure that if we do joint work, it's really our internal resources that do the work and not outsourced stuff. It's also crucial, by the way, to be able to have an objective view on the ecosystem, not being biased, but one way or the other. Okay, so I told you that we actually produce things in QUTAC, and the way we try to do that is that, well, we set ourselves up in working groups. I think this is not as special, but the heart of QUTAC really is those two working groups that you see on the left here. We have a working group focusing on material science. Clemens was just in the room. He's leading one of the working groups there, who do fantastic work in terms of doing quantum Monte Carlo type methods and benchmarking a couple of methods there, where 7 different member companies contribute really individual researchers to jointly basically advance the research. Actually, first paper was published in that field beginning of the year, so if you're interested in learning more, go check that out. And what we will focus on today, though, is the other working group called Working Group for Production and Logistics, where, as the name suggests, we have a bit of a different focus, but have 11 member companies, and I think by now it's about 25 to 30 people contributing. And yeah, I mean, it's fascinating, because when we started this 2 years ago, I was actually leading the production logistics working group, and it was bi-weekly meetings where, say, 2-3 people showed up irregularly. We were talking a lot, but nothing really came out. And now we have quarterly workshops with really 25-30 people joining, and have published 2 papers in the last couple of weeks. So that journey from really zero outcome to something that is really meaningful and valuable to all of us, I think is quite astonishing. We obviously also focus on political communication, which is a crucial part, but I think in order to be allowed to have a voice, right? It's not because you represent a big company that you should have a voice. It's because you prove street cred, if you will, right? You know a little bit what you're talking about, and I think that therefore these working groups really focusing on the applications are crucial. Right. So maybe let me give you a couple of details as to how we operate and how we go about things. So in our working group in production logistics, basically, we started, as mentioned, 2 years ago by trying to find a common language, by trying to basically get people together. And it's tough, right? Like we have people from computer science, from physics, but also product managers, researchers. Everybody has different interests. So how do you basically make sure that you come to a productive work setting? The way we did that is in the beginning to just collect individual use cases. Everybody tried to define them such that other companies and other industries can understand them, and thereby try to identify common research goals. And the outcome was that we ended up with 2 work streams. One focusing on logistic type problems. Their first research topic was to advance and benchmark different methods for solving knapsack problems. And a second work stream that Alex is going to talk about, focusing on quantum generative modeling. And yeah, as mentioned, 2 papers came out beginning of the year to show what we did. And before I hand over to Alex, just a couple of lessons learned to try to paint the story of how these consortia works actually produce value. It sounds very naive and straightforward, but communication is key for us. The game changer really was a workshop that we did in the middle of COVID. Everybody was remote, but nevertheless, we just got together. It was 15 of us by that time, and spent 2 days just coding together, setting up a joint repository, setting up working structures, setting up communication channels, and it's these simple things that sometimes really make the difference. Then finding a joint language, right? As mentioned, it's not easy to let a I don't know, computer scientist from SAP talk to a quantum chemistry expert from Böhringer. So how do you find the common ground? I think this is it needs a lot of work, but it's definitely worth the effort. And then most importantly, if you want for people to not only join the meetings a couple of times to kind of see what is happening, but to actually stick to it and to contribute, you have to somehow provide value for each individual company, right? They have to be incentivized internally, not by external managers basically telling them to join. And therefore, you really have to focus on the content and really provide meaningful research possibilities for each and every member. And how these different research artifacts could look like is something that Alex is going to tell you a little bit about.
All right. So thank you, Johannes, for the nice introduction. Am I mic up? It works? Great. OK, so thank you. As I said, thank you, Johannes, for the nice introduction. The recent QUTAC publication I want to talk to you about is called A Performance Characterization of Quantum Generative Models. So what you can see here on the right-hand side is a quantum generative model trying to learn. What you can also see is a measure of the goodness of the fit plotted over several different training epochs. How that one is defined, I will tell you in just a moment. First, I want to mention that generative learning refers to the unsupervised learning of probability distributions, such that when you actually use your models, you create samples which mimic in some form or another the training data you've put in. This is useful in cases where you want to amplify statistics of events which would be otherwise too rare for you to use, or when you want to plug them into existing design pipelines in order to, for example, perform drug discovery de novo. Quantum states already quite naturally represent probability distributions. I'm, of course, talking about the probabilistic nature of quantum measurement. And it may turn out that these probability distributions, which these quantum states represent, are hard to simulate on classical hardware. This leads us and many other quantum machine learning practitioners to the following hypothesis. It may be that quantum generative models can do better than their classical counterparts with respect to 3 very important points. So number 1 is the expressivity. How big is the function space you can map to for a given set of parameters? Number 2 is a possibly shorter training time. Of course, how fast do our models converge? And number 3 is the stability during training. Now, earlier today, our QUTAC colleague Clemens, he set the stage for me to argue a very important point, which is expectation management. So I want to do that as well. The fact, what we did in our paper was we didn't prove quantum advantage. We didn't even increase revenue by any one arbitrary percentage number. What we did was a methodological research. We performed benchmarks in order to guide quantum practitioners who are just breaking into this field of quantum machine learning, which compared to its giant cousin, that is classical machine learning, is still very much in its infant stages. Now, how did we do that? So, in total, we've performed over 1,200 experiments in order to understand the interplay of choices between the interplay of model architectures, data normalizations, and and training methods. And all of that had to start from some point. So what we started with, of course, is we defined some training data sets, and we normalized them in order to be able to use the same quantum circuit for every one data set. How these ones are defined, I will tell you as well in just a moment. First, I want to say that these data sets, which we've then first normalized, we've plugged into a classical generative adversarial network in order to just have a classical baseline to compare our results against. And the quantum models which we've trained and benchmarked are actually quite numerous, as I mentioned. So first, we differentiated between several different circuit architectures. Here we defined, or rather identified, the so-called continuous architecture and the discrete architecture, which we further subdivided into discrete standard and discrete copular architecture. We also differentiated between two training methods. One of them is the QCBM and the QGAM. Okay, so these are all just some random words I've just mentioned. At some point, I will have to start defining things, and that's what I want to do now. So the QCBM is the quantum circuit Born machine, and the QGAN is the quantum generative adversarial network. Two training methods, which are basically the two sides of the same coin. So effectively, what you do is you train a quantum generator, either using the QCBM, where you create samples. You plug them into histogram, you compare the histogram of the training data, plug them into a measure of the difference between these histograms, and compute a gradient-less update on your parameters. I'm saying gradient-less update because this histogram operation is non-differentiable, so you can't use things like automatic differentiation in this case. Where you can use that, though, is in the quantum GAN. So in the quantum GAN, the setting is, as I said, almost exactly the same. So you also start with your generator. You generate either continuous or discrete samples. And you, instead of plugging them into some histogram, you plug them into a discriminator, as you may know if you've heard about GANs before. And this discriminator then decides if it thinks the samples are real or fake, depending on these choices, and also if it thinks that the training data are real or fake. You compute updates on your discriminator and the generator separately. Now, as I said, the ways you get to your trained model are different, but at the end what you are left with is a trained quantum generator. And what I mean by that is that they are able to represent these guys. So what you can see here are two-dimensional scatter plots of our training data, which we've loaded into our models. I'm aware that they might seem simplistic to you, but it's their simplicity which allowed us to just immediately use our quantum models without having to rely on any additional classical compressions beforehand or autoencoding. And this also set the stage for us to tell you that there's no real difference, that there's no real effect on which classical models have in this context. Now, on the top row, you can see the data sets normalized with the min-max normalization, which is just a linear transform which scales and translates your data set such that it lies in a unit square. And on the bottom row, annotated with the shorthand PIT, you can see the probability integral transform. It has the same effect of transforming a data set to be in the unit square, but it does that in a very nonlinear fashion because it needs to do one thing which is very important. It needs to make the marginals uniform. And that is for such that we are able to use the discrete copular architecture. So the discrete copular architecture is a subcase of the discrete architecture, which is one way you can interpret a quantum circuit as a function. Because in order for something to be a machine model, of course it needs to be a function first. So the way we do it in the discrete architecture is we just basically perform a forward pass through the quantum circuit, measure all of our qubits at the end, and receive a bit string. And this bit string you can convert to a number and associate it with a point on your two-dimensional grid or three-dimensional grid. In the case of the min-max normalization, we use the so-called standard circuit, and in the case of the probability integral transform, as I've mentioned, we use the Coppola ansatz. And for the continuous architecture, it's similar but different in that way that the evaluation results we had are not just single measurements of our circuits, but expectation values, which we've computed using state vector simulations. On real hardware, of course, you can't do that. Instead, you just do many measurements and average them. Now, the output, if you're limited by the classical precision of normal classical computers, is a float. And importantly, in both cases of the min-max normalization and the probability integral transform, we used the same ansatz for both. What I want to just mention to you as well here in that case is that not the standard Coppola or the continuous ansätze were invented by us. These are all, of course, available to you. You can look them up, how they are defined in the paper later on. And everything I've just mentioned up to now leads us to, for you to be able to understand what you can see here. So on the left-hand side, you can see the two-dimensional results. And on the right-hand side, you can see the table of the best performed model. We've also had three-dimensional results, but they basically lead us to the same conclusions, which are the following. So if we vary the number of parameters as a metric of comparison between our models and look at the so-called Kullback-Leibniz divergence, which is a measure of similarity between probability distributions, which tells us the goodness of the fit, so how well our models did, we learned that the effect of the model architecture and the data normalization is much more important than the training method. Specifically, what I want to say is that the continuous architecture, the one which uses expectation values as evaluation results, does not seem to perform as well as expected. On the other hand, the discrete Coppola architecture is in some way the superstar. So in every case, it beat all other quantum models. But importantly, in the case of the stocks and the X datasets, it even beat the classical baseline while using up to 2 orders of magnitude fewer parameters. I just want to reiterate that one. So this relates to the point I've made earlier with the expressivity. In the case of the X dataset, the results were better with respect to the Kullback-Leibniz divergence by using so many less parameters. And this is, of course, very important if you think about like the recent progress in machine learning. Where has that been? So the recent progress of machine learning has been in just scaling the same models we've used for so long just to billions of parameters, hundreds of billions of parameters. And if you can reduce that and then scale them up again, you will get better results in the future. Okay, so what did we talk about? Effectively, what we've provided to you is another indication that QML methods, specifically quantum generative models, can do better than their classical counterparts for some very specific datasets, of course. For all of the datasets we've shown, the quantum models were able to fit the data arguably well for a few parameters. And in specific cases, they were able to do that while using 2 orders of magnitude fewer parameters. The case where that was is the discrete architecture using the Coppola circuit ansatz. And yeah, it also, as I mentioned, outperformed all of the other quantum models we've tested, we've benchmarked it against. Now, that's all for now. That's basically the essence of the paper. Our upcoming work, our upcoming papers will be concerned with the following. So we want to look at the same tests, the same benchmarks, but for higher dimensions. So we did the tests, as I mentioned, in 2 dimensions. We did them in 3 dimensions. We want to look if these results hold in higher dimensions, and also how the scaling behavior of the different training methods work. Because if you think about it for the QCBM, because you need to perform the histogram calculation, effectively what you are bound by is the curse of dimensionality, right? The hardness of this problem for the QCBM will scale exponentially with the problem. This will not be the case for the QGAN. We also we're also in the process of refactoring the code, which we've used in order to provide you these results, in order to release it to you, and then such that you can see for yourself. We are in the process of doing applications-oriented research, not really applications research in that regard, by using these discrete models in order to generate real-world tabular and patient data, for example, electronic health records, because we think these discrete architectures are very well suited for this task. And lastly, while doing all of that, we also are still doing fundamental research into circuit designs, And yeah, stay tuned for that for our next few papers. Thank you very much.
Okay, we have time for one question, if anybody has one.
Go ahead. Yeah.
Because you mentioned that you're going to go for the higher dimension later on.
Yeah, so there's a few different measures you can take, of course. You can measure, you can take a look at the difference in the marginals of the data sets. You can take a look at the Wasserstein difference, for example. And this is just an arbitrary choice we made because it's the most common in literature. Right? If you think about it, there are a few drawbacks to it, of course. I haven't, so earlier on in an earlier version, I had the formula on there where I could now argue that the Kullback-Leibniz divergence is a non-symmetric thing. So there's a difference if you compute the measure of similarity between the training data and the generated data, or if you compare the measure of similarity between the generated data and the training data, which is in that way some changes your values and might turn out to make the comparisons lead to different conclusions. But yeah, there's of course alternatives, and we've looked into them. But because of the let's say relation to the existing literature, we chose the Kullback-Leibniz divergence.